In this lecture, let us talk about the convolution sum and its properties. As I said earlier, we will mainly focus on linear time invariant systems. Okay, so this is a very simple derivation of what is famous now as convolution. You see, if the system has an impulse response h of n, that is you have an input del of n, give it to digital system, and the output is denoted by h of n, right? Then by invoking the time invariance property, del of n gives rise to h of n by invoking time invariance property, right? Del of n minus k gives rise to h of n minus k. If the system is time invariant, then you will get this expression, right? So this del of n minus k will lead to h of n minus k. So del of n gives rise to h of n by time invariance property. I got this expression. Now if I multiply this del of n minus k by a constant, okay, so let me multiply del of n minus k by, let's say, some constant a times del of n minus k, then this will give rise to what is called a times h of n minus k, right? So this is an example of the property called homogeneity. Okay, in superposition there are two things must be satisfied: homogeneity and superposition. If the input is multiplied by a, then the output also must be multiplied by a. So this a is a constant, input is multiplied by a constant, and the output is also multiplied by the same constant. Okay, now you take some signal like this, x of t. Okay, now we sample it. When t is equal to 0, you will get this value. T is equal to 1, you will get another value like this. Keep on do the sampling. So this value is a constant, right? As far as this signal x of t is concerned, this is constant at t is equal to 0, and this value is constant at the sampling instant. That value is constant at t is equal to 1 as far as the signal x of t is concerned, right? This is sampling instant 1, 2, 3 and so on and so forth. So what is this value? This value is x of 0. And what about this value? X of 1. And this one is going to be x of 2. And this is going to be x of 3 and so on and so forth. Right? So x of t, you give it to the sampler, right? You will get x of 0, x of 1, x of 2, x of 3 and so on and so forth. This x of 0 is constant at t equals 0, and x of 1 is a constant at t equals 1, x of 2 is a constant at t equals 2 at that particular time instant, right? Let's say capital T. Therefore in this expression, instead of multiplying this constant a, I am going to multiply by some other constant. Let me call x of k times del of n minus k, where k is a variable, doesn't matter. Substitute k is equal to 0, k is equal to 1, nothing, not a problem. Then this expression gives rise to x of k del of h of n minus k. okay, by using homogeneity property. Okay, so this is an example of the application of the principle of homogeneity, right? If the input is multiplied by x of k, output will be multiplied by x of k. Okay, now you apply the principle of superposition. Okay, so the whole idea behind this derivation is LTI system, linear time invariant system. So here we applied time invariance, and then we are applying homogeneity, and then we are going to apply superposition, because when I say linear, that means the system must obey homogeneity and superposition. Okay, so for this guy we are going to apply superposition principle. Okay, you apply superposition principle in order to get the output value. So del of n gives rise to h of n, del of n minus k gives rise to h of n minus k by using time invariance property, and then you apply what is known as homogeneity property. Okay, and then you finally apply superposition principle, right? So you take this guy and then sum this up, right? That means we apply all these inputs simultaneously, k going from minus infinity to plus infinity. You are not only taking only one input, you are going to apply many inputs, okay, like x of 0 times del of n minus 0. The output is x of 0 times h of n minus 0. X of 1 times del of n minus 1 gives rise to x of 1 times h of n minus 1, and keep on like this. You apply as many as inputs as possible. Summation of, that means superposition. You are doing the superposition principle, right? Therefore in compact form I can write summation of x of k del of n minus k, and where the k is from minus infinity to plus infinity. Then this gives rise to summation of same x of k h of n minus k, where k goes from minus infinity to plus infinity. Okay, now in the left hand side you look at where little carefully. So what do you observe from this? I already told you, this is my signal. Okay, instead of taking the continuous time signal, let me draw the discrete time signal. Let's say this is 2.2, then 2.3, 2, minus 1.5, 1.2, like that. So this is my discrete n, 0, 1, 2, 3, 4, like that. It's a simple example. Okay, so this 2.2, this point, how can I represent it? This is nothing but x of 0, and this one is x of 1, right? This is my x of n. No, when substitute n is equal to 0, you'll get 2.2. N is equal to 1, you'll get 2.3. N is equal to, you'll get a x of 2, and this one is x of 3, and this is going to be x of 4. Now you multiply this guy with an impulse. What will happen? You take impulse like this, like this. Now how do you represent this impulse? 0, 1, 2, 3, 4. This is del of 0, and this one is, what is that? You can write del of 0 or del of n, that's it, not an issue. Del of n. This is del of n minus 1. This is del of n minus 2. You substitute n is equal to, then del of 0 is 1. And this guy is del of n minus 4. Sorry, n minus 3. And this one is del of n minus 4. Now multiply, let's say this is figure 1 and this is figure 2. Multiply figure 1 and 2. What will you get? This is 1 and this 10th is 1. This all are 1. Right? So point by point you are going to do the multiplication. So here I have del of n multiplied with the x of 0. Right? So you will get what is called this sample point. So that is going to be x of 0 times del of n. And then multiply this guy with this guy. So what are you going to get? You are going to get this sample, and this is going to be x of 1 times del of n minus 1. Like that you multiply point by point, like this and that, like this. Okay, so maybe 1 minute, let me write down here. This is del of n minus 1 times x of 1. Then you'll get one more sample here, and this is going to be x of 2 times del of, let me write down here, x of 2 times del of n minus 2, and then you'll get one more sample. This is x of 3 into del of n minus 3, and so on and so forth. So you superposition everything. You will get x of 0 times del of n plus x of 1 times del of n minus 1 plus x of 2 times del of n minus 2 plus dot 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 dot. So after multiplication also, what is this del of n minus 1? It is 1, right? So in this expression, this is going to be 1 and this is going to be 1 and this is also going to be 1. When n is equal to 0, see this index and this index, compare these two indexes. When n is equal to 0, then this del of n is equal to 1. Here the index is 1. When n is equal to 1, then this also equal to 1. Compare this guy. When n is equal to, this also equal to. Therefore, after multiplication, essentially you are getting something, this figure 3. This figure 3 is the same as x of n. There is no change. Okay, nothing has changed. Here also 2.2 and this also 2.2. And this is 2 point, because this 2.2 is multiplied, this 2.2 is multiplied with 1. This 2.3 is multiplied with 1. What about this value? Yeah, this amplitude is multiplied with again 1. And this minus 1.5 is multiplied with 1. This 1.2 is multiplied with 1. So after multiplication with the magnitude of 1, again you'll get back the same magnitude. Therefore, the signal does not change once you do the multiplication with the 1. Therefore, the multiplication of figure 1 with the figure 2 is once again the same as figure 1. Therefore, this is nothing but x of n. Okay. So, this whole summation is nothing but x of n. Therefore, if I write in the compact form, x of k del of n minus k, where k is equal to minus infinity to plus infinity, this whole thing is equal to x of n. So that's what I want to write down here. So if you look at here, the left hand side is equal to what? X of n. Therefore, if you give x of n, my output is this one. Okay. So if you give x of n to a system, digital LTI system, my output will be summation of, what is that? It is here. x of k times h of n minus k. Where k is equal to minus infinity to plus infinity. Now generally if the input is x of n, we will denote the output by y of n. Therefore, output of the system is denoted by y of n, which is equal to summation of x of k h of n minus k, where k is ranging from minus infinity to plus infinity. Okay, therefore the left hand side becomes x of n. So an arbitrary x of n can always be expressed in this form. Okay, therefore the output must be equal to y of n, which is the famous convolution theorem. So this is the derivation of convolution theorem. Okay, so this is a convolution theorem, and this convolution theorem is derived based on the principle of superposition and time invariance property. Okay, so first we invoked time invariance, and then homogeneity, and then superposition. So for an LTI system, the output y of n is equal to summation of x of k multiplied by h of n minus k, k going from minus infinity to plus infinity. Now you do simple manipulation here. I mean by changing the variable, that is by putting n minus k is equal to r in the above expression. Then what is going to happen? Okay, one can easily show that this above expression as summation of k is equal to minus infinity to plus infinity x of n minus k times h of k. This is y of n. Simply you can not do this. It's a very simple exercise, so one can do that very easily. Okay, it's not a big thing. Like substitute n minus k is equal to r, then k is equal to n minus r. Okay, so that is the substitution. Now as far as the limit is concerned, when k is equal to minus infinity, then what about r? R is equal to n minus k, right? N minus of infinity is equal to r. Therefore r becomes plus infinity, right? Similarly, substitute k is equal to plus infinity, then r becomes minus infinity. Okay, so therefore this expression becomes y of n is equal to summation over x of k, k is n minus r, and h of n minus k becomes n minus k becomes h of r. Okay, now what about the limit? Limit is k is equal to minus infinity. What is k here? K is minus infinity, then r becomes plus infinity, so it is plus infinity to minus infinity. And this is summation, right? Summation you can change the limit, it's not an issue. So minus infinity to plus infinity, x of n minus r times h of r. Okay, where r is equal to minus infinity to plus infinity. See, when k becomes minus infinity, r becomes plus infinity as far as the limit is concerned. When k is equal to infinity, then r is equal to minus infinity. That is why the lower limit is plus infinity, upper limit is minus infinity. Now I interchanged it, right? So it doesn't matter as far as the summation is concerned. Now this r is a dummy variable. Once you do the summation, r will disappear, right? So in the final expression it contains only n. After all, r is a dummy variable, right? So you can simply change to some other variable. So replace r by k again if you want. Then summation of k is equal to minus infinity plus infinity x of n minus k times h of k. And this is my output y of n. And this summation is denoted in the literature as follows. X of n, you put a star symbol like this, and then h of n. So you put a star symbol to denote the convolution operation. So star stands for convolution in this particular context. Okay, like if the star is written above a symbol, like if I put a star like this, then the star indicates complex conjugate. Okay, if the star is written in the horizontal line, then it indicates convolution, and this is complex conjugate. Okay, now obviously these two summations are equal. Okay, this let me call this as 2, and where is it? This one, let me call this as 1. These two summations are identical. Therefore y of n you can write as summation of x of k times h of n minus k. K is ranging from minus infinity to plus infinity, or you can write x of n minus k times h of k. K is equal to minus infinity to plus infinity. Therefore, obviously the order of convolution is not important. Okay, because these two summations are identical, right? So in that case, either you can write x of n convolved with the h of n, or you can also write h of n convolved with the x of n in this manner. Therefore, this property is known by the name of commutative. Okay, so in other words, convolution is commutative. The operation of convolution is commutative. Now there are some special cases that we will encounter in practice. In general, our convolution is, mind you, this applies only for LTI systems. Okay, because we invoked in finding the summation the principle of homogeneity, principle of superposition, and also the fact that if the input is delayed by a certain number of samples, very beginningly we called this property. If the input is delayed by a number of samples k times, then the output also delayed by k times, k time units. Okay, so if the input is delayed by a certain number of samples, I mean k samples, then the output is also delayed by the same number of samples. Therefore, we have also invoked the property called time invariance property. So this convolution sum is valid for LTI systems. If the system is time varying, then also we can write a convolution summation, but it would not be h of n minus k, it would be something else. Okay, so this h of n minus k or x of n minus k will now be a function to be found out of n and k, but the argument will not be n minus k. So for a time varying system, we write instead of n minus k, we write n comma k. This is time invariant system. For time varying system, we will write x of n comma k, we will put comma n comma k comma h of k, or we will write x of k h of n comma k. So this type of systems you will find in the wireless channels. Whenever you want to model the wireless communication, whenever you want to model the channel, then the channel will keep on change with respect to time. So in such a case, the channel is modeled up by time varying system. So probably you'll be studying this in your wireless communication course. Okay. So anyway, that is beyond the scope of our course, at least for now. Okay. So we will mostly be concerned with the linear time invariant system. Okay. So y of n is equal to summation of h of n minus k. Let me write x of k first. Which should I write first? Okay, let me write down, no problem. X of k times h of n minus k, where k is ranging from minus infinity to plus infinity. Now let us consider a special case. The special case is, suppose the digital system is causal, right? Digital system is causal. In that case, your h of n is equal to 0 for n less than 0, right? If it is causal, then h of n equal to 0 for n less than 0. That is, before the input is applied, del of n arrives, there cannot be an h of n. If that is so, then this argument, okay, will become negative when k exceeds n. Okay, when k exceeds n, then that argument will be negative. If that is negative, then that is 0 for causal systems. Because for causal systems, h of minus 1 is 0, h of minus 2 is equal to 0, h of minus 3 is equal to 0, and so on and so forth. Now, when will you get this condition, negative argument? Negative argument arises when n minus k, right? When will it happen? When what can I say? When k exceeds n, right? That means what? K is greater than n. Okay, so that is the condition. When k is greater than n, then the argument will be negative. And therefore, the upper limit now should be restricted to small n. So no need to go to up to infinity. Say in this limit, where k starts from minus n, and it goes all the way to infinity. But when k is the running variable, the running index k exceeds n, this implies h of n minus k is identically equal to 0, because we assumed a causal system. So no need to do the summation up to infinity. So what you do is, you better stop the summation at n, because when k exceeds n, the argument is negative, then you are adding zeros. So no use of that. So therefore, let me stop at this point, and k is equal to minus infinity to n, x of k, h of n minus k. This is y of n, and this is for causal system. So whenever the system is causal, don't do the summation up to infinity. You stop your summation at n. Okay, therefore the convolution summation simplifies to k is equal to minus infinity to n. Okay, so now do you understand the logic, the reason? Beyond n, the argument of h becomes negative, which is 0. Alright, let's say the input x of n is causal now. This is first special case 1. Now special case 2. Now let's say x of n is causal signal. You know the definition. X of n is causal means What is the condition? If x of n is causal, then x of k, okay, no problem. I can put x of k also here, not an issue. X of k is equal to 0 for k less than 0. That is my causal signal. Causal system is different and a causal signal is different. Now we are assuming that causal input. Okay, what is x of k? It is an input. Now we are assuming input is a causal signal. If the input is causal signal, then what is going to happen? X of 0 is not equal to 0. It is not necessarily 0, right? Instead of writing like this, I can write x of minus 1 is equal to 0, x of minus 2 is equal to 0, x of minus 3 is equal to 0, like this. It goes up to x of minus infinity is equal to 0. Now you take this summation. What is going to happen in this summation? When substitute k is equal to minus infinity, what will you get? X of minus infinity times h of n minus into minus plus h of n plus infinity plus dot 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 x of minus 3 h of n plus 3, right, plus x of minus 2 h of n plus 2 x of minus 1 h of n plus 1 x of 0, right, let me finish this, x of 0 h of n, then plus x of 1 h of n minus 1, and so on and so forth. Now look at this in this summation. What is this x of minus infinity? As far as causal input is concerned, this is 0, and x of minus 3 is 0, x of minus 2 0, x of minus 1 0, right? I forgot to put plus here. And this is non-zero, x of 0 is non-zero. Therefore, when k is less than 0, my input is 0. So what is the use of doing the summation all the way from minus infinity to minus 1? No need, right? So you can get rid of that negative parts. Anyway, this x of minus 1 is going to be 0, x of minus 2 is going to be 0, x of minus 3 is going to be 0, all the way up to x of minus infinity is 0. So adding 0 doesn't make any sense. Therefore, instead of using the summation from all the way from minus infinity to n, you can simply put that summation as k is equal to 0 to n x of k h of n minus k. Now this summation is valid only for causal system. The upper limit is changed due to causal system and the lower limit is changed due to causal input. Okay, and this is the expression for y of n for an LTI system. Okay, so if the system is causal and the input is also causal, then our special summation becomes y of n is equal to summation of x of k times h of n minus k, where k starts from 0 and goes up to small n. It's very simple proof. Okay, in most cases this y of n this y of n we will use it, okay, but there is no reason why to a causal system you cannot apply to non-causal system. Okay, you can use this expression for non-causal signal also. I already told you this non-causal signal processing is used for recorded data, so you can use this convolution sum for recorded data and even for causal signal also. Okay, so this convolution sum formula can be used. This is important point. Convolution sum formula not only for a causal system but also for non-causal systems, and it can be used not only for causal signals but also for non-causal signals. It doesn't matter, okay, whether the system is causal or non-causal, or causal input or non-causal input. Okay, so this summation is valid for a linear time invariant causal system. Okay, so there is another qualification added, that is causal system and causal signal also. Okay, causal system and causal input, causal signal. At a given situation, you must write the convolution summation correctly, otherwise you will get wrong results. Okay, now let us see the properties of convolution. So we had already proved that convolution is commutative by changing the running variable x of n convolved with the h of n is equal to h of n convolved with the x of n. This is known by the name of commutative. And the next property is associative property. So x1 of n convolved with the x2 of n, you first do the convolution x2 of n with the x3 of n, and then you get some result, and that result is convolved with the x1 of n. This is the same as what you call, you first convolve x1 of n with the one second, yeah, convolved with the x2 of n, you first finish these two guys, then again you will get a result, and that result is convolved with the x3 of n, you will get the same result. This property is known by the name of associative property. And the third property is distributive property. This is all very easy to prove it, okay, it's not very difficult. x1 of n convolved with the x2 of n plus x3 of n, this is equal to x1 of n convolved with the x2 of n plus x1 of n convolved with the x3 of n. Okay, and this is called a distributive property. So the associative property tells you that if you have a convolution of three signals, let's say x1 of n, x2 of n, x3 of n, then the order in which this is carried out is not important. In any order you can do this convolution. Okay, in fact you can use yeah, same, whatever the order you like it, you can do it, nothing is wrong. In fact, I can write this convolution operation as follows: x1 of n convolved with the x3 of n, and then you can do the convolution with the x2 of n, not an issue. This is also valid. And this is called a convolution associative property. Okay, and the third property I already wrote down here, that is distributive property. Okay, so the convolution obeys the distributive property, and this property says that if you convolve x1 of n with x2 of n plus x3 of n, then it is equal to x1 of n convolve with x2 of n plus, it is here, plus x1 of n convolve with the x3 of n. So you have two convolution here, sum 1, convolution sum 1, and here you have one more convolution sum. But here you have only one. Okay, so this is the distributive property, and the proofs, as I said, are extremely simple. Okay, so that's all about convolution in sum of a given system. Okay, if the input is x of n, then the output will be convolution sum of x of n with the convolution of x of n and h of n. Okay, so this derivation is based on linear time invariant property, and this derivation is derived based on the two properties. One is time invariance and then linearity principle. Okay, so let me stop at this point. In the next lecture we will discuss some problems. Thank you.